undergrad, I also didn't do it, right? It wasn't until my advisor, in a really wonderful Italian accent, called me a moron. He didn't really call me a moron, but he made me feel like a moron. And he basically berated me about not doing this, right? And I was like, wow, I've learned something there, right? How would you be able to tell if you're in the linear range of absorbance? So you have a cuvette, you have a sample, you pop it in, you get an absorbance value. How do you know you can trust that you're in the linear region? Thinking that you're a chemist. Yeah, cool. Oh, thank God. Yeah, stand up. I'm sorry. Seriously, stand up. Everyone look at Colton, for God's sake. He got it right. Applause. Yes, applause. Thank you, sit down. I know I embarrassed the hell out of you. Your girlfriend's embarrassed just vicariously, and now even more embarrassed. Sorry, Michaela. This is better. It could be worse. You could be embarrassed by him for other reasons. Yeah, you're right. And more importantly, I've said this like 50 times in lecture, right? If you have a value and you're like, gee, I wonder if I'm linear or not, or worse, your boss goes, are you in a linear range? And the subtext of that phrase is cool, right? You go, yeah, because I diluted it. Now, Colton said several times, which is even better than I was going to suggest, but just dilute it once. Because, for example, if you have an 8 absorbance and you dilute it tenfold and Beer's law is working, which it would not, by the way, in that region, then your value would be 1/10 of that, correct? 0.8. And I'd bet money, not a lot of money, I like money and I don't want to give it to you, but I'd bet $50 actually that you could not make an absorbance 8 solution, dilute it tenfold, and ever once in the universe have it actually be in the linear range. I would bet $1,000. That's how confident I am in that. Not more than that, because that's $1,000 is a lot of money, right? More to you than to me, but still a lot of money, by the way. That's like, half my mortgage payment, right? Or like weeks of groceries. $1,000 to you is like PlayStation money, right? You get a pretty sweet PlayStation, some games, some controllers, right? Is that still feasible with $1,000? I don't know. All right. So how to check? Dilute. You can just do it once even, right? Absorbance is generally not linear above an absorbance of 2, right? That's 99% being absorbed, right? That's 1% transmission. So you've got almost everything gone at that point. Think about it this way. If you made $2 million a year, would you consider yourself pretty wealthy? If that's your salary, yeah, right? What if you made $8 million a year? How much better would your life be? Would it be 4 times better? Probably not, right? Maybe you think so, but trust me, there's a tapering off at some point, right? What if you made $80 million? Is there a difference? I mean, maybe in the size of yacht you have, but really, you own a yacht, right? People are buying your groceries for you at some point, right? Like Mackenzie Bezos is giving away most of her money. She's still going to have like $1 billion. She's not a problem, right? She's going to be fine. Don't cry for her or her children or great-grandchildren. They've got a lot of money, right? Same thing goes in the bottom end of the spectrum. If you've got 3 kids and you've got $8 in your bank account, and you've got no income coming for 2 weeks, that sucks. If you have 8 cents in your bank account, it's not any better or worse, right? It's 0. So absorbance has a very limited range over which it works, right? And partly because of this idea that Beer's law deviates because at this sort of point here, everything's absorbed, right? Some of you will come to my office and say, Dr. Pavlis, what is the absorbance value for things to become absolutely thick or not? It actually depends on the absorptivity. So in other words, a highly absorbing molecule hits optical thickness, so to speak, before a molecule has a low absorptivity. Right? It's the product of concentration and the absorptivity. And the absorptivity is constant for the wavelength you're looking at, right? So the way we check that is we do a dilution. It could even be just a single dilution, right? More often you have to do more than one because the first dilution shows you're way off already, right? To get around the other things absorbing, a perfect blank. Well, what about this idea we talked about before, sorry to scroll back up, that you're measuring scatter and reflection and absorbance, right? We typically don't worry about reflection too much, but you have to account for it at some level. You have to account for scatter, right? Just when we talk about like a Lubbock dust storm is not a good day to measure the absorptivity of nitrogen in the atmosphere, right? Because you've got something else absorbing. The thing about Beer's law is that it's trusted by so many people that don't actually remember this lecture, or they took my class or anyone else's class like it, or they never learned it. And so if I might digress because it's Friday and I feel like it, I'm just going to tell you a quick story about, so one of my jobs at NASA, in addition to being a scientist and running a lab and all that other stuff, was whenever someone came with a proposal to get research funding and they hit like a certain level of interest, like maybe they'd gone for a few rounds of proposals and now NASA was thinking about funding it. And these are substantial grants. They'd call in a few of us, some of the group leaders in our division, who had a reputation for being hard asses, part of my language, right? To sit in and ask questions. And I was sitting there, and this guy was talking about making a device that would measure metabolites in urine for astronaut health. Because in the old days of spaceflight, you went up for a day or two or a week, and you came back down. And so if something happened funky, we just wait, right? And the assumption was we had the healthiest people on Earth going up there. Well, it turns out that astronauts lie about their medical history, so they don't want to get disqualified from flight. Also, when you're going up there for 6 months or 3 years, now the recurrence of kidney stones is a bigger deal, right? Or a potential for detached retina. Because if you get really sick on the space station, what you would do on going to the walk-in this afternoon to get a shot of penicillin costs 20 million US dollars to launch a rocket to come get you, right? So it's not like something that we think about. So they were trying to develop a system to measure metabolites in urine, and it was all through absorbance. And he's like, and the guy said in his seminar, money's on the line, right? Like $10 million contract probably. I don't know the amount, but it's of that magnitude, let's say. And he's like, the beauty of this is we don't have to even calibrate concentrations because of Beer's law, right? So we know the absorptivity is the analytes. We can just measure the urine, and I can tell you the concentration out in any calibration curve. And you should have seen, like, I believe I may have thrown my pen, like in disgust or something like that. That's what I do in meetings when I'm super pissed. I take off my glasses when I'm really angry. That shit gets real. Like, I didn't know I did this, and I took my glasses off, and I was like, oh no, like what? It's like you took off your glasses. Every time you do that, someone gets like the scientific beat down. I'm like, I don't know why I take my glasses off. I can't see very well without them. But apparently they come off. Like, it's like a hold my earrings kind of moment, I guess, for me. I don't know. And so like the glasses come off, and I'm like, well, you're measuring urine. Urine is a turbid medium. There's a lot of light scattering components in urine, right? And in space, you're going to have more crystalline material in your urine because kidneys don't work the same. And they're like, well, that shouldn't matter. And so I'm like, well, are we talking about optically thick materials? I started asking this stuff when I'm talking about in this lecture, and they're like, and they walked out with no money. I saved you $10 million, taxpayers. You're welcome, right? Because the assumption that Beer's law works like that is idiotic, right? And they were a bunch of biologists, and they didn't really understand chemistry, so I'm not going to crap on them. Just like I don't understand biology as well as they do, right? But I felt like they should have talked to a chemist, perhaps an analytical chemist, beforehand, and maybe had an answer to that question. It was such an elementary thing, it broke down their entire premise. The whole point was this little device, you put some pee in it, and you get an answer, right? It sounds attractive, doesn't it? But if you're relying on absorbance, you're saying, well, if I just measure the absorbance, I've got the concentration already because I know the absorptivities. That's a huge flaw, right? The last thing about Beer's law I want to harp about is monochromaticity. I do have to wonder, by the way, if my lectures are as entertaining at home. I feel like they're not. Let's just say, for example, right, what I'll call a monochromatic case. I like to draw these out because it makes a lot of sense. Okay. So I've got wavelength, and I've got absorbance in red, or blue, geez. And then in red, I've got just intensity, right, of the light, of my light source. Let's say that I've got like an LED, for example, right? Just for example. And then I've got an absorbance band that looks like this. All of the light that's emitted by that LED can be absorbed by that molecule, correct? So in this case, it's monochromatic, which is good. All right, so this is the good case. Makes me a happy scientist. Because all my light's being absorbed. Let's look at a case that's not monochromatic, though. This is bad. Makes me sad, right? So I've got absorbance and wavelength. Now here's my absorbance band, same absorbance band, same scale. But let's say I've got a really broadband light source that I don't filter very well. The regions I'm shading here are not strongly absorbed. That's intuitive, right? That light falls outside of the absorbance band of the molecule, right? Well, now let's write equations for this, right? I know that's the most exciting thing you ever hear a professor say, like, let's write an equation. The transmission in the monochromatic case is equal to the transmitted intensity over the incident intensity. Straightforward. In this case, the transmission is equal to the incident intensity plus a fraction f of the transmitted intensity, where this is the non-absorbed fraction, because it lies outside of the band of absorption, divided by I0. The bottom equation has a constant in the numerator that is now no longer related to concentration. It's not related to light scatter. It's not related to any of the assumptions that we were worried about. It's just light that gets through, right? It's kind of like having a rain gauge that is also attached to a dripping faucet, right? And you're like, oh, I got 3 inches of rain yesterday. Did you? Because you've got two inputs, if you will, right? So we need to get rid of that non-absorbed fraction. I have never in my life measured the output band of my absorbance instrument relative to my absorbance band. Does that make me a bad scientist? No. All right. I can set it, and so I know what it is, but I've never actually measured it. But a lot of people don't set it. They just go with it. People walk up. Absorbance, y'all, is one of the most common scientific measurements, right? It's like pH or temperature. People use UV vis in so many fields outside of chemistry. You work in the drug field, you'll be doing UV vis. You're an organic chemist, you do UV vis, right? We all use, it's a workhorse staple measurement, and nobody does it right. Nobody measures it, right? I can't tell you how many times I've read a paper where someone has said, yeah, I just measured the absorbance and not gave me the concentration just because I used Beer's law. And I'm like, you didn't calibrate it? Like, that's like meeting someone on the first date and deciding you're going to marry them. It doesn't probably work very often, right? Buddy Holly did that with Maria Elena Holly, and I assume they wouldn't have stayed married if he hadn't died in a helicopter crash, right? Terrible. Is it a helicopter or a plane? Is it a plane? Yeah, it's a plane. Sorry, I should know that. I'm not disparaging Buddy Holly. I'm just saying, if you came home and you're like, yeah, I had a date last night, we're getting married, your parents would be like, what? Like, trust me, I would. They're like, are you an idiot? I would say it nicer than that. Like, are you an idiot? So you have to be really careful with Beer's law, right? People use it, and I say this not just that you don't make these measurements and look foolish and not get your NASA grant because some jerk in a suit asks you a lot of hard questions, but because you're going to actually, as a scientist, in some way, shape, or form, you're going to be a scientist. I don't care what you want to do. If you're a doctor, guess what? You're going to get data that is UV vis derived, right? If you're a dentist, right? Absorbance is very important in dental curing, like the curing of dental materials. You have to understand these concepts and get them right because there are literally lives on the line sometimes, right? I harp about Beer's law a lot, but I mean, you know, it's important to understand. Imagine if pH only worked in a very small subset of data, right? So let's talk about UV vis instrumentation because there are further limitations when you start thinking about how these things are measured, right? By the way, I was in a PhD defense a long time ago where a student was like measuring, he had developed nanoparticles that would like take drugs out of the bloodstream. The idea is like, if you OD'd, right, you could give these nanoparticles, they would pull like fentanyl into them, let's say, and then they're large enough that your renal system filters them out. You just urinate out this nanoparticle, right? So it's like it's kind of like a sponge. And he used UV vis to show that like he had cleared out all the drug because it went from like, you know, a millimolar down to like undetectable. UV vis has horrible limits of detection. So I asked him, I'm like, you used the least sensitive method to show that there's no drug present. And this is a drug that's still bioactive at very low levels, right? So you didn't really clear it out. You probably got 90% of it gone, which sounds really good until you realize there's still plenty to kill you, right? It just maybe prolongs your overdose somewhat. He did not like that answer. for that question. Neither did his professor, but I don't care. All right. So in the case of UV-Vis, you need a lamp, some kind of light source. It could be an LED or a broadband lamp. Then you need a monochromator to select a particular wavelength. And the reason for that, again, is that we need that monochromaticity. We need to have a band of light that is narrower than our sample, so to speak. Then you need the sample itself, which is always going to be some kind of cuvette these days. And then a photodiode. We use photodiodes because when there's no analyte present, the signal is large, right? And as the analyte increases, the signal goes down. But the blank itself has a lot of photons going to the detector, right? You can switch this up a little bit. You can actually have the light source, the lamp, or whatever it is, the LED or lamp, go into the sample first. So S is sample, right? Then to a monochromator. And then to a photodiode, right? You get the exact same answer in both cases. This one allows you to use arrays if you want, so you can use an array detector. The top one you can't. They give you the same answer because it's a straight beam. It's just a beam of light at a particular wavelength. So you can pre-select the wavelength and see what's absorbed, or you can let everything go through and see one wavelength at a time how much is absorbed. It's the exact same question, right? I can see how much money you spend per month in your bank account, and I can't, but if I could, by either seeing how much money goes out, or I can measure your balance before and afterwards, right? I get the same answer. Okay. The problem with this approach, or with UV-Vis in general, is that the signal decreases as concentration increases. So what does that mean, right? It means that noise is kind of problematic at both ends of the spectrum. So this is another really popular exam question for me. If I plot noise increasing on the x or y-axis against absorbance on this axis, so higher noise is bad, so I want a low value, right? I get a curve that looks like this in what I call the student instrument, the one we let you use in freshman lab. And then in the big kid instrument, when you're a grad student or a scientist, right, it's a little bit better on the high end. But really, absorbance is only useful between the value of about 0.2, approximately 0.2 and 0.9. That's sort of the region of low noise. This region here. Going back to the idea that Beer's law kind of works, going from 0.2 to 0.9, and let's round up from 0.2 to 1.0. What concentration range is that if Beer's law is working linear? If you go from an absorbance of 0.2 to an absorbance of 1, or in reverse, how much is your concentration changed? Assuming that Beer's law is working that day. Rebecca. These numbers, it's 0.2 and 0.9. Yeah. So going from 0.2 to 0.9 and round up to 1.0. All right, I'll make it easy for you. Five times. How did you get that number? Yeah. I mean, you know, 0.2 is 1/5 of some value, and 0.2 of 1 happens to be 1/5, right? So it's a 5-fold concentration range. Think about that for a minute. Beer's law only works over less than a 10-fold concentration range. Think about pH. What is the concentration range, roughly, that you can handle over pH? Let's assume that there are no acid or sodium errors. It's a 10 to the 14th range. A little bit more than that, right? That's 100 trillion-fold change in concentration. Absorbance can do 5. That's much smaller than 100 trillion, correct? One is slightly larger than our national debt, and one is the cost of a Chick-fil-A sandwich. correct? Things to think about, all right? National debt. So what causes this curve to be like this? And it's really the noise factor, right? At this part, at low absorbance, is transmission high or low if the absorbance is low? Transmission high. Thank you so much, Eric. Yeah. If transmission is high, then what you are doing is measuring a small change in a large value. And unfortunately, light source flicker is the dominant source of noise, as I mentioned before, in the ultraviolet and visible, right? That's the major source of noise. So your light source noise is the major contributor at low absorbance. And that is regardless of whether you have a good instrument or a bad instrument. The difference between a good instrument and a student instrument, so to speak, like the old Spec 100 in the 1307, 1308 labs, or even the papercraft spectrometer that one of you made, just one of you in class, right? The difference is going to be that the detectors and electronics are better. The light sources are the same. An LED is an LED. There's no like super fancy LED or no super fancy tungsten lamp. They're all just the same, okay? So on the high end of the spectrum here, out here at high absorbance, T is small, right? To go with Eric's answer in the opposite direction. So you're measuring a small value, measuring very little light. Since the transmission's high at low absorbance, we have to use photodiodes because they handle large signals. And they're bad at measuring small signals. So you have detector noise out here. This is the problem of measuring anything that has an inverse signal relative to the concentration. Anytime your signal decreases as a function of increasing concentration, you have an optimum region you can work at. So you can't go too high or too low. If your signal increases with increasing concentration, that's a different and easier problem to solve, right? But in this case, you're kind of screwed either way, right? If it's too high, there's not enough light to detect, so you're gonna have noise. If it's too low, it's measuring a very small change in a large value, and that doesn't maybe seem to you intuitive like a problem, but it's actually a very noise-prone difference, okay? Because the small changes in concentration start to look like the long-term fluctuations in the light source. Make sense? I spent a lot of time on Beer's Law, an entire lecture he integrated over 2 days, because it's that important, because it's so commonly used. It is going to be one of the main detectors we use in separations, right? Most separations have a UV-vis detector system on them, right? Especially in liquid chromatography. And all of these things still apply, right? So it's important to understand. I'm going to skip double beam instruments because they're kind of archaic. And I want to move on to my favorite type of spectroscopy, and that's molecular luminescence. And when I'm talking about molecular luminescence, I'm really talking about fluorescence. There are different kinds. It's the GOAT of spectroscopy, okay? I'm just going to say it. I know, like, Grandpa's using slang again, but I don't care, right? It is amazing. You can measure large concentrations, and you can measure single molecules. And the last time I checked, that is the ultimate limit of detection, whether you have a molecule or whether you don't, right? You can't go at a lower concentration than that. And not only measure concentration, but fluorescence can actually tell you things about the environment in which that molecule is residing, like its hydration or solvation state. Sometimes it's pH or even the local temperature or viscosity of the fluid around that individual molecule can be ascertained. You can even look at two molecules interacting with each other on a nanometer or angstrom scale, which you can't do by other methods, okay? So it's really useful. So we already talked about fluorescence in some way, right? It's relaxation to the ground state or via photon emission. So first you absorb, and then you give off a photon. And as I mentioned before in the beginning of spectroscopy, most molecules don't do this. How do most molecules dissipate energy? Yeah, vibration, right? Internal conversion, vibration. Heat. A small subset of molecules will actually give off a photon. I'm going to give you an example. I really ticked off one of my organic colleagues one time inadvertently because I drew a molecule on the board that I wanted my student to make, and I was like, just go make that. It seems like it'll work. He's like, it's not that simple. And I was like, I'm sure it isn't. And then my student made it because she was really talented and it worked like the first time. And so it's not a brag about me, but rather my student was really, really good. But I think, you know, I've only made one molecule in my life. And if I say me, I was a professor, so I told my student to do it. And so it just happened to be luck that the one time I did it, I drew it on the board and said that should probably work. It did. So we'll look at this molecule, for example. And sorry, I drew it back and backwards. All right. And I've shortchanged myself a bunch of double bonds. So this molecule is a Nile red derivative. Nile red is the sort of main part here. This molecule's job it's a fluorogenic probe. Normally, we attach an amino acid here, or amino acid sequence. So I'm just going to draw or kind of diagram out different parts of the molecule. Yep, quench. Okay, let's look at this molecule a little bit, right? Just to point out what it does. This section here, oh, that was terrible. Why did I do that? All right. This section here is just for water solubility. That's the whole point, right? Those sulfate groups sulfide groups rather, are just there to make the thing soluble in water. This amine group, if you attach an amino acid sequence of them, I usually would do short peptide sequences, makes the molecule non-fluorescent. And we actually use this as a probe to look at single cells undergoing what's called programmed cell death or apoptosis in my lab years ago. This is a project from about a decade ago. So we had a grant to make this molecule and use it. So we would put this molecule with a peptide sequence that match what are called caspase enzymes. They're the enzymes that dismantle your cell when your cell is going to die intentionally, right? And so they cleave off a very specific sequence of residues. And so we make, that peptide sequence, throw this into a cell. It's cell permeable in that state, and it's non-fluorescent. And then when these enzymes become active, they cut off that amino acid sequence, and you're left with this molecule that is now fluorescent. We were able to actually look at single molecules of this being produced in a single dying cell. So you could focus on the cell, and it's totally healthy. You give it a drug to make it die, and then one by one, these molecules start to appear, almost like on a constellation, and you could get incredibly fast temporal dynamics of the cell suicide process. You have all heard about apoptosis before or cell death? Anyone not heard of it? Hold up your hand. Anyone have webbed fingers? You did as a fetus. You know why you don't have it anymore? Because that tissue got a signal to die off, right? It's the engine of menstruation. Sorry, everybody, but it is. So, the endometrial lining grows. No baby is produced this month. It's like, dang it, let's reset. And so all that tissue gets a signal to die off through apoptosis, and then menstruation occurs, right? So it's an incredibly important thing to study, and cancer cells are really good at avoiding apoptosis. You can tell it it's time to die, and it's like, I'm good. I'm going to keep dividing. It's like talking to my 14-year-old son. I ask him to do anything. He's like, I'll do it later, as he plays video games on his computer, and then it never gets done, right? And I go through this farce every single day on some level, right? So, this cancer cell doesn't listen. So let's look at the fluorescence section, though, because that's what's really important. That fluorescence section has a couple really important category or things about it, right? First off, it's rigid, correct? rigid and planar. It has pi conjugation. These are required for most fluorescents. There are some outliers, but if you're making a fluorescent molecule from scratch on the drawing board, you are going to aim for a small structure, a drug-like structure, in fact, that is rigid and planar and has pi conjugation. In fact, when we add those amino acid sequences, they disrupt that, they sort of delocalize that, that pi network, right? They disrupt it. And that's why the molecule becomes non-fluorescent. And as soon as you start cleaving those, then it returns to its fluorescent state. So a lot of times, you can make a molecule temporarily non-fluorescent by basically disrupting that pi network. Or if there's an axis of rotation, right? So if you think about it, no internal rotation. That's what I mean by rigid and planar. If there's a carbon-carbon single bond in this network somewhere, that maybe between the two pi groups, they can rotate relative to each other. That also disrupts that delocalized network of electrons. It's basically kind of like a metal, right? And a metal has a delocalized network of electrons on its surface, right? And that's the same thing that happens in this case, right? If the network is too large, like graphite, it doesn't work, right? So it's got to be smaller. One of my students right now, how many of you have lab on Friday in this class? I have lab. You have Michelle as your TA. Michelle makes, and actually Meg makes it too, little tiny graphene carbon dots out of soot. So Michelle comes to my house and we burn tiki torches in my backyard and we collect the soot off of them because it's really good for making nanoparticles. And they're tiny little, basically pi networks, and they're highly fluorescent, right? So you need a rigid, planar, pi conjugated object to be fluorescent. How many of you have heard of the green fluorescent protein before? GFP? Really? You've heard of it? What do you know about it, Eric? Nothing, but you've heard of it. Good. Well, you're ahead of everyone else. The green fluorescent protein is actually a jellyfish protein that is fluorescent. It's green, so hence the name. Its discoverers got a Nobel Prize not because it's fluorescent, but because they found out that you can put that, it's metabolism-independent protein synthesis. It's one of those genes that you lock out, that an insect can make it, and a plant can make it, and a human can make it. Every single living thing that has protein-making machinery can make that particular protein. So you can make a glow-in-the-dark rabbit, or the glow-in-the-dark bacterium, or the glow-in-the-dark cancer cell, right? A fluorescent programmed molecule. The large protein itself, it's like 65 kilodaltons. It's a big molecule. Is not fluorescent. There's actually a tiny little center in this protein that is a small, rigid, pi-conjugated molecule that is actually doing all the fluorescence work, right? The rest of the protein is just there to exist as sort of like backbone and structure, if you will. But the actual fluorescence is a tiny little center of the molecule that basically has these characteristics, right? So when we talk about fluorescence in the beginning of the semester, or beginning of this class, we talked about the idea that you have like absorbance, right? And you have like internal conversion, which is heat or vibration. Then you can have fluorescence, and then you can also have triplet state, you know, and then phosphorescence, right? We talked about all of these things. So there are, and then quenching also. So this is a crappy diagram of what we talked about before. There's one fluorescence path, that's my point here. And there are many other pathways to the ground state. Imagine, if you will, that say Duncan's committed a horrible crime. Horrible crime. He's on every news source right now. And we know very credibly that he's going to Chicago next, right? For the next phase of his plan. And I pick an interstate between here and Chicago, and I just set up a dragnet for him. Am I likely to catch him? Duncan says no. Why? Yeah, take another road, right? Is there more than one way to Chicago? Sure. Can you take a plane, train, car? Which car route do you take, right? Which plane route do you take? Which plane do you get on? There are multiple paths. So fluorescence is that one path that I'm monitoring, if you will. And there are other ways a molecule can sort of escape that path to go around it. So we use a term called the quantum yield to describe this. It's different than quantum efficiency. Quantum yield for fluorescence is actually equal to the rate of fluorescence. And these are measurable and or known quantities, right? I say right, I'm telling you right now they are. Okay, so that's more like a okay versus asking you if you use already. Divided by all the rates to the ground states. You can have fluorescence, you can have internal conversion, you can have external conversion. I'll label these, okay? And you can have inter-system crossing. So this is triplet stuff, right? Right here. This is quenching. This is vibrational relaxation. And this is fluorescence again, right? A quantum yield of 1 means that the fluorescent rate is the largest rate by far. All the other things become negligible, right? Then you have Kf over Kf, which last time I checked, X over X is 1, right? A molecule that we call non-fluorescent doesn't mean that it's not capable of fluorescence. It means that the other methods, like quenching and vibrational relaxation and intersystem conversion to triplet states, are more favorable, okay? In fact, in fluorescence, sometimes we can actually mess with this. So oxygen is really good at quenching. So you can take a cuvette in a fluorimeter and measure its fluorescence and then breathe over it and displace the oxygen if you do this long enough, and you'll get a larger value for the same concentration. If you bubble nitrogen through it, same effect, right? So this quantum yield can change. It's indicative of the environment, but it's kind of a given thing for a certain rate. So we talked about this before, is that some molecules are fluorescent and some are not. It comes down to this quantum yield. And there's no great cutoff. It's not like we say above a quantum yield of X, it's fluorescent or not. There are molecules that we call fluorescent that maybe have a 0.1 quantum yield. So 10% of the time they give off a photon, and 90% of the time they don't. That's a fluorescent molecule for sure. There are proteins that we use that have 98% or 0.98 quantum yield. So they almost always give a photon, right? They're much brighter, but they're both fluorescent materials, right? So, all right, it's going to get touchy here, but it's like being a college student, right? You can have a college student with a 0.8 GPA or a 3.8 GPA. They're both college students. One has had a different level of success than the other. I'll put that charitably, okay? So I don't want to end lecture on a comment about GPA because people get squirrely about that, but just think about that for a minute, right? So we're going to talk about fluorescence, instrumentation, and measurement on Monday. We have our next exam on the 9th of April. It feels like I just wrote an exam. It feels like you just took one, but that's how this class works, right? All right, so have a good weekend. Stay out of trouble.
Dr. Pappas,
Yes.
I had a question about how to tell if it's optically thick, optically thin. So you said to do the dilution. When you do that, are you just looking for the linearity? Or something
Exactly,
else?
yeah. So if you're measuring, a value of X, your absorbent, and you do a tenfold dilution, your new absorbent should be 1/10 of that value. If it's not, then you're not in the optically thick range. You may have to do a couple more dilutions to get the true concentration.
Okay, thank you. That makes sense.
Thank you. Bye. Yes.
So between these two diagrams, is the only difference is one is an array photodiode, and the other one's a single one?
Well, this could be a photodiode or an array. In this setup, you can use either type. In this setup, you can't use an array detector.
Oh,
So you can use a photodiode or array. It just depends
for
on
the second one?
Yes.
Awesome, thank you.
Yes.
Treating the target acid in wine
Yeah,
today, were you able to grab the target?
I didn't really need it today, so I couldn't grab it.
Where
But
did I get that?
I mean, I think it probably doesn't, but like, I think to have it. Think of card. You take a card, I think when it's tiny, it's just right into it, but fine enough. Or if you have a wine for crystals on it. I didn't really need to say that over on it. I still have to. Okay.
structure has to be rigid. But could you have it where, like, where the rotating forces around, so, like, it's not gonna rotate because spiritually hindered? Would that just be, would that what this will have to do? So, there's a, you ever heard of a